So I've shown you the mouse one about comparing groups. This one is about compost and growing lobelia on it. It's exactly the same process as doing the mouse one, apart from there's only 4 groups in this case, and the other one was more complicated. So what I can do is to analyze, compare means, and I'm just going to show you one way ANOVA, the standard way to start with. So we've got weight and we have compost, and I'm going to do the post hoc analysis as I showed before on Bonferroni. Do continue and press OK. So the only thing I wanted to do this for is to get these multiple comparisons, to show all these particular p-values and numbers, and to show you that the F statistic is 5.755 and the significance 0.03, and these values are the sum of the squares and the mean of the squares. And I just wanted you to see the ANOVA table and the data table. So that's the standard way of doing a one-way ANOVA. So now we're going to use an alternative, which is going to give me exactly the same result, but is the first example I'm going to give you of what's called the general linear model. So when I go to analyze, instead of going to compare means to do the comparison, I'm going to go to the general linear model. Now, the general linear model covers regressions where you have, so if I was going to fit a line of height against weight, and I thought that gender affected the slope of the line, what I could do is a different weight against height line for each of the different genders and compare them to each other. So that's called analysis of covariance. So it's how is a regression affected by a categorical variable such as gender. So that is another example of a general linear model. Now the ones we're going to do, and the only ones I really think you need to consider, well, I suppose you might do multivariate. So univariate, we've got one outcome variable. You've got multivariate, where you've got multiple outcome variables, and then you've got repeated measures where you take the same individual and you do multiple measures on them. So instead of it being a paired example, so you've got a before and after, if you did multiple different measures from the same individuals, then that's called a repeated measures, and it's repeated measures ANOVA. I would strongly suggest that you never actually use that method, because there's another way of doing it which is not repeated measures. If you ever need to do repeated measures, come and talk to me. Let's stick with univariate. So if I click on univariate, I get a different kind of window which is asking me a load of questions. Now the box is dependent variable, that's your outcome. Now this is a very simple data set, so I've not got a lot of choices here. That has to be weight. Now I have 2 boxes here which are fixed factors and random factors. So a fixed factor is the thing that you're doing the experiment on, your experimental conditions. So in this case, it's your compost, which is varieties A, B, C, and D. Before it was the mouse diets, low pro and whatever else. Now, there's another box here which is random factors. So this is what I would use if I was supposed to be doing repeated measures. I would put the identity of each of the participants in the experiment as a random factor. So that is called a mixture of fixed and random factors model. A mixed model, basically. If I had weight against height, so I had a regression line that I wanted to fit multiple regression lines dependent on some fixed factor such as gender, then I put that in covariate. So that's what the 4 different boxes mean. For doing ANOVA 1 or 2 way, the only thing you're going to use is the fixed factor box. So you pop, in this case I've only got 1 fixed factor, so I'll put it in the box. Now you can specify, if you've got a complicated number of factors, how you build a model, but we don't need to do that. As before, you've got contrasts, so you can pick what you want to compare to what else. You've got plots, which will give you a sort of regression plot of your different factors. In this case, it makes no sense to do. And then you've got post hoc analysis. So you can do post hoc tests for compost. And again, we want to click on Bonferroni because that's the one we did last time. And these are the marginal means. Just wondering if this gives you anything useful. And if I do compare main effects and click on Bonferroni, I think this should give me the same table as I'm getting for the post hoc. And that's it. Press OK. So this has done the general linear model of comparing those 4 different compost things, their weights to one another. So what it's trying to do is fit a regression line as a horizontal straight line to see if the means are the same in all of them. So it's got an intercept and it's got an effect which is to do with compost. So ignore the intercept because, as in usual with any kind of regression model, the intercept is arbitrary and pointless and not needed. At the top here, it's got the sum of the whole model. This is the strength of the whole model once it's been corrected. And you'll see it's exactly the same as the line for the compost, because in this case, the only thing that the model's based on is compost. So if you see the numbers 26.8763, 8.599, 5.755, 0.03. If I go up to my one-way ANOVA table, that is the between groups one-way ANOVA table. It's then got a line which says error, which is 5636 1.577. And if you go back here, that is the within groups value for the ANOVA table. And then it had corrected total, which is 82.6 and 39, which is the total from the ANOVA table. So this is the same data as comes out in the ANOVA table, but with a little bit more complicated things. Okay, it's done estimates of the means for each of the different groups. And then it does pairwise comparisons that we asked for. So I asked for the pairwise comparisons as post hoc, and I got 0.03, 0.45, and whatever. And these are exactly the same as the ones I got from post hoc doing the one-way ANOVA. I also asked it, so that's the post hoc table. I also asked it to do the EM totals. So these are the EM totals, the pairwise comparisons. And I asked for Bonferroni, so it's exactly the same as the post hoc table, which is exactly the same as the post hoc table from the one-way ANOVA. So these things are exactly equivalent. I've just used 2 different mathematical approaches to do it. In fact, if you look at the univariate tests table here, this is a subset of this table here and happens to be most of the ANOVA table that's here. So you're getting the same numbers, just in confusingly different presentations to one another. Now, that was a set of data where I didn't have to use the GLM. I could have just stuck with using a one-way ANOVA because it only has a single variable that's important. So now I'm going to open the Cosmos dataset. So this one is more complicated because it has the compost, and then there's 2 different varieties of plant, Cosmos plant, one called Pip, the other one called Christopher. So what you want to know is the compost still having the same kind of effect, or does the variety also have a role as well? So again, we go to Analyze, go to General Linear Model and Univariate. There is one dependent variable, in this case it's height and not weight, and there are 2 fixed factors, which is the compost and the type of Cosmos, whether you've got Pip or Christopher. Let's ignore model. It does have some subtle things that you can do with it. Let's ignore contrast, let's ignore plots. We can do post hoc tests. We can only do them for compost because you can't do them on variety because there's only 2 varieties. Post hoc tests need to have more than 2 groups to check between each other. And I'm going to click on EM means because I want to look at these things. So when you've got a model and it's got 2 variables, what you've got is to consider the effect of compost, the effect of variety on the height, and the effect of compost multiplied by variety. So your model can include an interaction between the compost and the variety. So it might be that one of the varieties grows better on one compost, whereas the other variety grows better on a different compost. So those interaction things need to be calculated. And I can compare main effects and do Bonferroni, but this will just give me exactly the same table as I did in post hoc. So I press OK, and I get my results. Now, this is a more complicated example. So let's ignore the corrected model and the intercept for a minute. So what you can do is see the effect of compost. So in this case, the significance of compost is 0.285. So this is showing us that compost is not making a significant difference to the height of the plant, but the variety makes a big significant difference to that. And then compost multiplied by variety again is not significant. So the only thing that's making a genuine difference between the 2 different groups is the variety. And if you look at the pairwise comparisons and you look at the sig values between all the composts, you can see there's no difference. So in this particular case, the results have shown there is a difference in height between Pip and Christopher, and the size of the confidence interval is, so Pip against Christopher is 3.75 to 7.26 difference in height, whereas Christopher to Pip is minus because one of them's taller than the other. This is their significance, so it's 0, so there's definitely an effect of the varieties, but there's nothing in the composts in terms of differences, because there's nothing significant here. So that's the two-way ANOVA. One thing that I could have shown, and when I was doing that and click on, so it's worth doing a plot to have compost on the horizontal axis and variety as separate lines. And I need to add that and yeah, do it as a long line chart and put error bars on it and do continue. So this would have shown me visually what I've just explained through the tables, which are not so convincing. This shows you visually that if you look at the composts, it's almost a horizontal line. So between the 4 different composts, for Pip, which is blue, and Christopher, which is red, there is some variability, but there's quite a lot of overlap between the error bars of each of the different composts. But you can see that the red line and the blue line do not overlap with each other, and the confidence intervals from the red and blue line do not overlap with each other, apart from in compost 1. So this is telling you that variety has a significant difference and compost doesn't matter. And you could see that purely visually.